Calculus, video 64, antiderivative examples. So in this video I have several examples that I want to share with you, and I have separated those to kind of 5 different categories. So in the last video we learned about undoing the power rule, and so the first category of antiderivatives is just a few more problems on undoing the power rule. Okay, and in the very last example of the previous video, we talked about where the integral of, say, a over x dx, you cannot use the power rule for that. Instead, the integral of a over x dx is a times the natural log of the absolute value of x plus c. And so a few more problems on integrating a over x, or some constant over x dx, to get a times the natural log of the absolute value of x plus c. And also discuss why do we have to have the absolute value of x on that problem. Third, antiderivatives of exponential functions. So we know how to take the derivatives of exponential functions. How do we undo that? How do we take the antiderivative of exponential functions? 4 antiderivatives of trig functions, and 5 antiderivatives of inverse trig functions. What you're not hearing me say is how to undo a product rule, or how do I take the antiderivative to undo a product rule. We're not quite there yet. Right, we're also not quite there as far as how do I undo a quotient rule. What's the antiderivative to undo a quotient rule? Not quite there yet. So right now, these are the 5 categories of antiderivatives that we'll be able to do. So let's start with more on undoing the power rule. I recommend that you go ahead, pause the video, see if you can work these. Once you get down to either an answer or getting stuck, come back and watch the video for how to work them. So go ahead and pause the video, try it yourself, and then come back. All right, so the first thing I'm going to do for this antiderivative, and you see the integral symbol here, which means we're taking the antiderivative, is I'm going to rewrite this in the same way I would have done if it was taking the derivative. So the cubed root of x, that is the same as x to the 1/3, plus I have 6 divided by the 4th root of x. So the 4th root of x would be x to the 1/4, but it's in the denominator, so I'm going to bring that to the top, leave the 6 up here, bring the x to the 1/4 to the top as x to the negative 1/4. All right, so we're going to rewrite these radicals in the rational exponent form. That allows us to now do the power rule. They're undoing the power rule, really, where we're taking each one, we're adding 1 to the exponent to undo the power rule, and then dividing by our new exponent. So it looks something like this. X to the 1/3, add 1 to that, and you get x to the 4/3, and then divide by the new exponent 4/3. Plus 6 times, add 1 to negative 1/4, adding 1 to negative 1/4 gives you 3/4, and then divide by my new exponent 3/4. Don't forget to add the constant of integration c. Okay, and if I simplify here, I get, so dividing by 4/3, that's the same as multiplying by 3/4. X to the 4/3, plus 6 times, dividing by 3/4, that's multiplying by 4/3, x to the 3/4 plus c, or 3/4 x to the 4/3 plus, let's see, 24 divided by 3, it'd be 8 x to the 3/4 plus c. Don't forget the plus c at the end. Right, that is the antiderivative. I'm not going to check these, but you could check this. You could take the derivative here and see that you end up with x to the 1/3 plus 6x to the negative 1/4. Okay, moving on to number 2. Looks pretty straightforward. The integral of 7 dx, we're looking for what is the antiderivative of 7. All right, our function there is 7. What function, if I took the derivative of it, would give me 7? Right, pause the video, work it out. All right, When we think of 7, we can think of that as 7 times x to the 0, right? Because anything with the 0 power is 1. So adding 1 to that would be now x to the first. So this is 7x to the first divided by the exponent of 1. Don't forget the plus c, otherwise known as 7x plus c. The derivative of 7x is 7. The derivative of c, 0. So that one's it. It's done. Number 3. What if it's not x? What if the variable we have is like theta, or t, or beta, or y, or something else? The important thing to note here is the variable that we're using is theta, but we're also taking the antiderivative with respect to theta. So those are the same, and that's important for us. So we're going to treat it like it's an x, basically. We're going to do the power rule. We're going to add 1 to the exponent. So now this is 6 times theta to the third. We're going to divide by our new exponent of 3, and then plus c, for a final answer of 2 theta cubed plus c. And if you took the derivative of that, with respect to theta, you would get 6 theta squared, and that's what you have as your original function. So if that one works. So notice if I have a 6 theta squared d theta, I'm getting a theta in my answer. All right, very good. We're rolling right along here. What if you wind up with something like this? The integral of 2x minus 5 times x squared plus 1 dx. I've already talked about earlier here that we're not quite ready for how do you undo a power rule yet. Product rule yet. So we're not going to try to do some product rule thing. Instead, when you see something like that, just go ahead and distribute. Take the 2x times the x squared and the plus 1. Take the negative 5 times the x squared and the plus 1 and get individual terms. Right? So we're going to rewrite this one as the integral of 2x times x squared, that's 2x cubed. 2x times 1, that's 2x. Negative 5 times x squared is negative 5x squared. Negative 5 times 1 is negative 5. All in parentheses dx. Don't forget your dx there. Now you don't have to do this next step, but I'm going to write them in order, just because I like to. 2x cubed minus 5x squared plus 2x minus 5 dx. And now I'm going to undo the power rule. I'm going to take 2x cubed, that's going to be 2x, add 1 to the exponent 4, divide by my new exponent 4. Minus 5, add 1 to the exponent, so 2 plus 1, 3, divided by my new exponent 3. Plus 2x, add 1, or the exponent here is 1, add 1 to that, that's 2, divided by my new exponent 2. Minus 5x plus c. And if I simplify, I get 1/2 x to the fourth minus 5/3 x to the third plus x squared, because the 2's cancel, minus 5x plus c, and that is my antiderivative. You'll notice that when we have a polynomial, like we have here, 2x cubed minus 5x squared plus 2x minus 5, when we do the antiderivative, the degree of the polynomial will go up by 1. And so instead of having a degree 3 polynomial, we now have as an answer here for the antiderivative a degree 4 polynomial. Okay, last one, I believe, of these power rule, or undoing the power rule. Anytime you're dividing by what's called a monomial, a monomial is a single term. Right, we're dividing here by a monomial or a single term. Just a t to the 3 halves, or a 5t to the 3 halves is still a single term. You are not adding or subtracting anything in that denominator. Right? We can't undo quotient rules or anything like that. So instead, because we're dividing by a monomial, let's just separate the numerator as 12t to the 8th over t to the 3 halves minus t over t to the 3 halves, and try to simplify that before taking the antiderivative. Okay, so when we have t to the 8th divided by t to the 3 halves, that's like subtracting, right? You can do 8 minus 3 halves, 8 minus 1.5. and you get the integral of 12 times, you can use decimals here, that's fine. 8 minus 1.5 would be t to the 6.5. Nothing wrong with decimals. Just want to make sure that looks like a 6.5, not a 6 times 5, 6.5 there. Minus, okay, here I have a t to the first minus t, or divided by t to the 3/2. So 1 minus 3/2 would be negative 1/2. So I get t to the negative 1/2, or negative 0.5. All right, let's do the antiderivative. We are going to power rule now. So we're going to add 1 to the exponent. So I get 12t to the add 1, 7.5, divided by my new exponent, 7.5, minus t to the power of, if I take negative 0.5 and add 1, that's now positive 0.5, dividing by my new exponent, positive 0.5. Don't forget the plus c. All right. Let's see, 12 divided by 7.5, that's, I should probably know that. 12 divided by 15 over 2, 24 over 15. I can call that, what, 1.6, if you will. So 1.6 t to the 7.5 minus, dividing by a half is like multiplying by 2, so 2t to the 0.5 plus c. All right, there we go. And again, you could take this derivative, right? You do the derivative here, you should wind up back with this same 12t to the 6.5 minus t to the negative 0.5. Oh, I was wrong. I said that was the last one, but there's one more. What if it's not a monomial? Right, our denominator here is not a monomial. What do we do? Well, you could separate everything into like 2x squared over 2x minus 3, 11x over 2x minus 3, 21 over 2x minus 3, but we don't yet know how to take the antiderivative like that. So what we're going to do is hope that the numerator factors in something cancels out. That's our hope. We hope that the numerator factors. Otherwise, we're going to be in trouble here. Now, there is another way you could do this. Because it's a linear factor, we could actually use synthetic division here. But I'm going to think that the numerator here will turn into a factored form. So, the numerator is 2x squared plus 11x minus 21. Right, so if I do like my AC method here, that's needing two numbers to multiply to negative 42. That's the 2 times the negative 21. And add to the 11. Things that multiply to 42, like 7 and 6, 14 and 3. 14 and 3 seems like it might work. If I have a positive 14 and a negative 3, that multiplies to negative 42. A positive 14 and a negative 3 adds to 11. And so I get 2x squared plus 14x minus 3x minus 21. Basically the 11x here is splitting up into 14x and negative 3x. Right? A little line here. So what do the first two terms have in common? They have a 2x, leaving me with x plus 7. The next two terms have a negative 3 in common, leaving me with x plus 7. We want those parentheses to be the same. And we get 2x minus 3x plus 7. So it does factor. But not only does it factor, it factors into 2x minus 3 times x plus 7 over 2x minus 3. Well, what can you do with the 2x minus 3's? You can cancel them. Simplify them, if you will. They simplify to 1 over 1. So then you have the integral of just x plus 7 dx. And this is something we can easily solve. We do the antiderivative. We add 1 to the exponent, so it was already x to the first, and now it's x squared, and divide by my new exponent 2. Plus 7x plus c or 1/2 x squared plus 7x plus c. So if it's not a monomial, at least for right now, let's hope that numerator factors. All right, more with this integral, the antiderivative of a over x dx, or you might see it in this form as well. You might see it as the integral of ax to the -1 dx. It means the same thing. In either case, you get a times the natural log absolute value of x plus c. So before I guess we get into doing more problems, the question is, we'll come back to this one over here. The question is, why do we get the absolute value? Why is it natural log of the absolute value of x? Right. Why absolute value? All right. I'll try to explain it in graphical form. The graph of y equals 1 over x, right? That's our a over x, or just to make it easy, 1 over x, looks like this, right? Y equals 1 over x looks something like this. And what you'll notice is this function is defined for positive values of x, like 3. You can plug in 3 and get 1 over 3, but it's also defined for negative values of x, -3. You plug in -3, you get -1 over 3. So the function is defined for both positive and negative values. But when we graph y equals the natural log of x, what we notice is y equals natural log of x is only defined for x greater than 0. Looks like this. There's that vertical asymptote at 0. It's only defined for x's that are greater than 0. That's a problem because my original x's could have been negative. So in order to allow for that, what we do instead is we use y equals the natural log of the absolute value of x. And what that does is y equals the natural log of the absolute value of x. Now that allows for the x to be both positive and negative. If x is -3, then the absolute value of -3 is 3. The natural log of 3 gives us the y value there. And you end up with this curve here. You end up with the regular natural log of x curve as well as the negative side of things. In other words, you can plug in negative x's and now get out an actual answer when you do the absolute value, the natural log of the absolute value of x. We can plug in -3 because natural log of absolute value of -3 is the natural log of 3, and we can get the y value. So we need that natural log of the absolute value of x to allow us to input both negatives and positives values of x, which is how our original function was defined. It was defined both to the left of 0 and to the right of 0. Okay, so when we do the antiderivative for the integral of a over x dx, we need a times the natural log of the absolute value of x because this x could have been negative. Could have been negative. And if it was, then having the natural log of a negative number is undefined. Therefore, we have to make that absolute value of x there. Okay, so now that we know that, let's remind ourselves the integral of 7 over x should just be 7 times the natural log absolute value of x plus c. Let's do one that's a little bit harder. Like, lots harder. What about the integral of 3x cubed minus 6x squared plus 5x minus 4 divided by 2x squared? This should remind you of this problem up here. There's a single term in the denominator. There's a monomial in the denominator, and if there's a monomial in the denominator, what we do is we take the numerator, we separate it, and write each term of the numerator over that single term in the denominator. That's exactly what we want to do for this problem. I have a monomial in the denominator, so I'm going to write every term in the numerator over 2x squared. So 3x cubed over 2x squared, 6x squared over 2x squared, 5x over 2x squared, 4 over 2x squared. Right? So it's going to look something like this. we're taking the integral of 3x cubed over 2x squared minus 6x squared over 2x squared, parentheses for all of this, plus 5x over 2x squared minus 4 over 2x squared dx. Now please simplify this before you try to take the antiderivative. You don't want to take the antiderivative in this form. But we get the integral of 3 over 2, x cubed on top, x squared on bottom. That cancels, 2 of the x's cancel out, and you're just left with x. Okay, that doesn't look too bad. Minus 3 times x squared is canceled, just minus 3. Plus 5 over 2, x to the negative 1, if you will, or 1 over x, if you'd like that better. Minus 4 divided by 2 is 2, and then it's x to the negative 2 dx. Now, for 3 of these terms, we're going to use the power rule. But for the 5 over 2x to the negative 1, right, 5 over 2x to the negative 1, that's the same thing as 5 over 2 times 1 over x. The integral there is going to be 5 over 2 times the natural log of the absolute value of x. So be careful on that one. Right, so we get 3 over 2, add 1 to the exponent, now it's x squared, and then we'll divide by 2, the new exponent. Minus the integral of 3 is 3x. Plus, here's our weird one, 5 over 2 natural log absolute value of x. Minus 2 times, add 1 to the exponent. So the exponent is negative 2. If you add 1, you don't get negative 3, you get negative 1. And divide by negative 1. Don't forget the plus c. Okay, let's see if we can simplify here. 2 is like 2 over 1. So instead of dividing by 2 over 1, let's multiply by 1/2. So this is 3/2 times 1/2 times x squared minus 3x plus 5 over 2 natural log absolute value of x. Negative 2 over negative 1 is positive 2x to the negative 1 plus c. So 3/4 x squared minus 3x plus 5/2 natural log absolute value of x plus 2x to the negative 1 plus c. Right, I like these problems where you get all of this power rule stuff, but then with one of the terms you have to integrate to get to that natural log absolute value of x. All right, let's move on to antiderivatives of exponential functions. So, recall a couple of things. The derivative of e to the x is e to the x. But the derivative of 3 to the x is itself 3 to the x times natural log of 3. All right? Let's keep that in mind as we're doing these problems here. So the antiderivatives of exponential functions, if the derivative of e to the x is e to the x, then the antiderivative of e to the x is e to the x. If you're going backwards there, you just wind up with what you started with. So the antiderivative of 5e to the x is 5e to the x, but then it's also plus c. Can't forget that constant could have been there. All right, that doesn't seem too hard. We like e to the x's. It's a little more difficult if it's 3 to the x. Right? So just remember the derivative of 3 to the x is itself 3 to the x times the natural log of 3. Okay, but what we want to do is we want to take the antiderivative of 3 to the x. We just want to take the antiderivative of this. We don't have the natural log of 3 over here anywhere. There's no natural log of 3. So let's divide it out over here. And let's do this. What is the derivative of 3 to the x times 1 over natural log of 3? That would be 3 to the x times natural log of 3 times 1 over natural log of 3. And those would cancel out, and you'd have just the 3 to the x. So what I'm saying is when we take the antiderivative of 3 to the x, we get itself 3 to the x, but we have to then divide by the natural log of 3. We get this. The antiderivative of 3 to the x is 3 to the x times 1 over natural log of 3 plus c. And the reason is, if you took the derivative of this, if you took the derivative of 3 to the x times 1 over natural log of 3 plus c, you would get itself 3 to the x times the natural log of 3 times that 1 over natural log of 3, derivative of c is 0. Those cancel out. That's just 3 to the x. That's the exact same thing that you have right here. So when you're doing the antiderivative of an exponential and it's not base e, you need to multiply it by 1 over the natural log of that base. All right. Moving right along. 2 things left. Antiderivatives of trig functions and antiderivatives of inverse trig functions. And for those, let's just recall. Just to remind ourselves of the derivatives of trig functions. What is the derivative of sine of x? What is the derivative of cosine of x? What is the derivative of tangent of x? Right? Derivative of sine of x is cosine x. Derivative of cosine of x, negative sine of x. The derivative of tangent of x, secant squared of x. We'll pause here. What this means is, remember, the antiderivative is the undoing of the derivative. This means that the antiderivative of cosine of x dx is sine of x plus c. It's going backwards. The forward way here, that is the derivative. Going backwards is the antiderivative. So the integral, or the antiderivative of cosine of x dx is sine of x plus c. All right, similar argument. If the derivative of the cosine of x is negative sine of x, that means the antiderivative of sine of x dx, well, I don't have the negative sign here, the negative sign sign, so let's move that to the other side, and we get negative cosine of x plus c. The antiderivative of sine of x is negative cosine of x. And the reason is, the derivative of negative cosine of x is negative sine of x, which is just sine of x. So the derivative of negative cosine of x plus c gets us back to the sine of x function. Right? The derivative of negative cosine of x plus c gets us back to the sine of x function. All right, and finally, since the derivative of tangent of x is secant squared of x, that means the antiderivative of secant squared of x dx is tangent of x plus c. So we should know those. It's just undoing the derivatives. You just kind of have to watch your negative signs a little bit. All right, similarly, let's keep going here. I'll come back to this problem in just a minute. Similarly, since the derivative of secant of x is secant x tan x, that means the integral of secant x tan x dx is equal to secant of x plus c. Just undoing the secant of x derivative. Okay, since the derivative of negative, that's not what I want. Since the derivative of cosecant of x is negative cosecant of x cotangent of x, that means that the integral of cosecant of x cotangent of x dx is negative cosecant of x plus c. And finally, since the derivative of cotangent of x is negative cosecant squared of x, we get that the integral of cosecant squared of x is negative, dx. I lost my dx there. I don't want to do that. The integral of cosecant squared of x dx is negative cotangent of x plus c. We need to know those as well. Right, so here we have the integral of 3 secant x tangent of x. So you're asking yourself, what trig function has a derivative of secant x tangent of x? Well, that trig function is secant of x. And then you do the plus c. The 3 just hangs out. Right? Because the derivative of 3 secant of x would be 3 secant of x tangent of x. Right? Number 2, we'll take these in pieces. So we'll just first look at the cosecant squared. What trig function has a derivative of cosecant squared? That would be cotangent. But the derivative of cotangent is negative cosecant squared. We don't have the negative over here, therefore the negative must go on the cotangent of x. The derivative of negative cotangent of x is positive cosecant squared of x. Plus, now let's look at the cosine. What trig function, if I take the derivative of it, gives me cosine of x? That is a positive sine of x, and then plus c. And that's how we do the antiderivatives for trig functions. Finally, antiderivatives of inverse trig functions. There were 3 that I cared about the most. That would be the derivative of inverse sine of x, the derivative of inverse tangent of x, and the derivative of inverse secant of x. And the reason was because these had positive derivatives, whereas the other 3 had negative derivatives. The derivative of inverse sine of x is 1 over square root 1 minus x squared. The derivative of inverse tangent of x is 1 over 1 plus x squared. And the derivative of inverse secant of x is 1 over x square root x squared minus 1, with the x an absolute value. All right, that means if I want to undo these, we get this. This ends up being pretty important for us. I know it's our last part of this video, but this is really important stuff. The integral of, or the antiderivative of, 1 over square root 1 minus x squared dx, that's the derivative of the inverse sine of x. Therefore, this is inverse sine of x plus c. We need to know that. Similarly, the antiderivative, or the integral of 1 over 1 plus x squared dx, since the derivative of inverse tangent of x is 1 over 1 plus x squared, the antiderivative here is the inverse tangent of x plus c. Need to know that. And finally, the integral of 1 over x square root x squared minus 1 dx is equal to the inverse secant of the absolute value of x plus c. Okay, we need to know those. Let's try a couple examples and call this very long video to be over. Here I have the integral of 4 over 1 plus x squared. We should recognize that is the derivative of an inverse tangent. Now that 4 can just kind of come out. We haven't talked much about this, but if I have a constant times something, I can actually bring that constant out in front of the integral. All right, and now I have the 4 times the integral of 1 over 1 plus x squared. That would be 4 times the inverse tangent of x plus c. Done. Let's do one more. The integral of 6 divided by the square root of 1 minus x squared. We should recognize that as like 1 over the square root of 1 minus x squared. That's the derivative of inverse sine. I can bring the 6 out here. That's 1 over square root 1 minus x squared dx. That is 6 times the inverse sine of x plus c. Once again, done. The hard part here is recognizing that pattern to see that is the derivative of an inverse sine, or the derivative of an inverse tangent, or the derivative of an inverse secant.